Our next talk is on doubly efficient batch verification in statistical ZK, and Or will give the talk.
Thank you. Okay, so hi everyone. I'll present the work doubly efficient batch verification in statistical zero knowledge. This is a joint work with Mon Watblum and Pashan Vasudevan. So let's begin with a motive and example. Let's say there's a prover that holds a long list of RSA public keys, and he wants to convince some verifier that all of the public keys are well-informed. That actually means that each one of them should be a product of exactly two primes. Now the dot seems to have connected to the brace for some reason, but that's okay. Now, so the trivial solution for this problem would be for the prover to just send the cake factorizations, right? But as cryptographers, we don't like this solution because we'd like these prime factors to remain hidden. So let's try to use some zero knowledge proofs. So they were introduced by Goldwasser, Mikani, and Vakov, and we've already heard of them in this conference, so I'll skip the definitions. Okay, I see some other problems here as well. I'll just say for this work, we'll focus on statistical soundness and statistical zero knowledge. So that essentially means that we want soundness to hold even against computationally unbounded provers, and zero knowledge should hold in a sense that the output distribution of the simulator should be statistically close to real interactions between the honest prover and the verifier. So we work in the information theoretic setting. Okay, so when we talk about these kind of protocols, it's worth mentioning SDK. So it's the class of all problems that have such proofs. And when I say problems, I just mean problems that are defined by two disjoint sets. For example, our RSA public keys problem, the S instances will just be numbers that are products of exactly two primes. And this class is a central class that captures many problems in cryptography. For example, our RSA public keys number, our RSA public keys problem. And it has a rich structure and was extensively studied, for example, in Vadan's PhD thesis, which is highly recommended, at least by my thinking. Okay, so let's look on some possible solutions, trying to leverage zero knowledge proofs. So here there are another GMR, so it's Gennaro, Michiancho, and Rabin. They presented non-interactive statistical zero knowledge proofs for verifying that a number is a valid RSA public key. And the proof is essentially, again, non-interactive, so we have just one round. And again, we need, in order for this to make sense, we need to allow some access to a common random string. And in our case, it will be a uniform random string. And that's usually the case when we talk about non-interactive proofs in the SDK setting. Their proof has both statistical soundness and zero knowledge, which is what we focus on in our work. And the prover can be implemented in polynomial time given the prime factors, which means there's some chance that our protocol might have some practical applications. So that's nice, but this only works for a single instance. And we asked about k instances. So what can we do? Of course, we can just multiply everything by k, right? The length of the common random string will be multiplied by k, and the number of proofs the prover will send. This is still non-interactive, and the only problem is that now the communication scales linearly with k. And we would like to achieve something better. We can use other efficient zero-knowledge proofs that already exist, for example, Kinnan's protocol that we've also heard about in this conference. But these kind of proofs will achieve computational soundness or computational zero knowledge, whereas we want to get statistical security guarantees. So let's try to look for other solutions. There's a line of works that concluded with me et al. That presented non-interactive statistical zero-knowledge proofs for verifying k instances with communication that is only polylog in k for all of NISCK. So you can take some proof, some problem that has an NISCK proof and convert it to be a batch proof with very nice communication complexity in terms of k. So essentially, now we have k instances, maybe no longer RSA public keys, but some k instances from a general NISDK promise problem. And again, we have a single message and a common random string. And here I'll stress that both the size of the message and the size of the proof should be polylog k, not only the size of the proof. So they're both short. And yeah, so not like the previous presentation where we stressed we wanted to get also a small CRS. Now they're both small, so we don't need to handle that. The problem with the proof, some problem is that the prover runs in exponential time, and of course we don't like it that much. We'd like to get polynomial time provers. Okay, so let's try to look at doubly efficient batch proofs. So they are essentially proofs that also do batching, but in this case, we require the prover to be doubly efficient. That means that we want the prover to run in polynomial time given the k witnesses. And their proof, essentially there was a long line of works concluding with a paper by the Rothman brothers that showed such doubly efficient proofs for all of UP with the same communication complexity as before, also polylog k. And UP here means just the subclass of NP where yes instances have unique witnesses. For example, again, our RSA public keys problem. Of course, yes instances are just products of two primes and factorizations are unique. So this problem belongs in UP. The problem with this protocol is that it is not zero knowledge. So we'd also like to somehow overcome this caveat. But in terms of communication complexity, we might hope to achieve even communication complexity. Maybe in the future, the Rothman brothers will publish another paper that will get better communication complexity. Okay, now let's get to our result. Yeah, I know it was a fine joke. Okay, let's get to our result. So we take the batch proof by the Rothman brothers that does batching for UP. It is doubly efficient and not zero knowledge. And the batch proof by Mu et al. That does batching for NISDK. It is statistical zero knowledge, but not doubly efficient. And we combine them to a new protocol that does batching for every problem that is both in UP and in NISDK. It is doubly efficient and statistical zero knowledge. So I'll state it a little more formally. Every problem that is in both of these classes has a public coin statistical zero knowledge protocol for very fine k instances, each of length n, with the following parameters. The communication complexity is as before, notably polylog k. The number of rounds is polylog n and k. The verifier runtime is quasi-linear in k times poly n. And here, we really couldn't hope to achieve much better verifier runtime in terms of k because the verifier has to at least read the k inputs in the statistical setting, statistical security setting. And the honest prover should run in polynomial time given the witnesses, polynomial in terms of n and k. So that's the double efficiency requirement. Let's see some other properties of our result. So it's a non-conditional result. We don't need to assume anything in order to construct our proof. And this is somewhat common in the SDK setting. The security guarantees both the soundness and the zero knowledge are information theoretic. And applications of this proof include the prime products example that we've seen, quadratic residuosity, and more variants of this problem. Okay, but if we could talk about computational soundness or computational zero knowledge, and then there are better solutions in terms of communication complexity. So you might ask, why do we even care? So I'll state some reasons. First, paranoia, right? If we know that our protocol has information theoretic security, then we don't need to be afraid of any big monster that will come and break it, no matter how computational power it has. We usually need the assumptions, so we don't need to be afraid that someone will break our assumptions. There's potential for better efficiency because we don't need to use some crypto-heavy machinery, so we might be able to make it more efficient. And it also furthers our understanding of SDK, or in our case, of NISDK, which is just a nice subclass. Okay, so I'll get to we don't have much time, but I'll try to go a little over a technical review. So we start with the RR20 UB batch proof. And essentially, the prover, given the k witnesses runs in polynomial time, this happens to be a public coin proof, so the verifier's messages are just random coin tosses. And we can clearly see that this is not zero knowledge because some property of their proof is that at the end, some witnesses are sent in the clear. So this is not zero knowledge. We would like to convert this protocol to be zero knowledge without blowing up the communication complexity. So essentially what we do is use the commit and prove paradigm of Benor et al. So first, we let the prover commit to our messages instead of sending them in the clear. So that's the first step. And then in the second step, the prover proves in zero knowledge that if she were to open the commitments, then the underlying messages would have convinced the verifier to accept. That's the second step. And the whole challenge here is how to apply this transformation without blowing up the communication complexity. So we first ask, how can we get communication complexity, good communication complexity for the commitments? And in order to do that, we take the mu et al. Proof and reduce it to efficient commitments in terms of communication complexity. Actually, instance-dependent commitments, but I won't have time to get into that. And we also need to care about the communication complexity of the zero-knowledge proofs. And to get good communication there, we use the Shai et al. MPC in the edge paradigm, and also some other maneuvers, and we can get this proof to have polylog k communication complexity, which is what we wanted. Okay, so thank you.
Any questions?
Can you generalize this proof for all SAK languages, like SAK intersect UP?
Yeah, so if that's actually an open problem. We don't know how to do it yet because the problem is essentially with generalizing batch proofs even for SDK, even if we don't talk about UP or things like that. Even for an inefficient prover, we don't know how to get a batch proof for SDK. It's like an open problem.
Any other questions? Okay, let's thank the speaker then.